When I think of vectors, I think of airplanes and pilots, right? So a vector, first of all, is a quantity that has both a magnitude and a direction. Well, a plane is flying on its path, right? So it has a vector, right? It's going a speed and it's going a certain direction. And then there's a wind vector as well, right? Depending on the speed of the wind and the direction of the wind, that's going to affect the flight path of the plane and the speed of the plane. And that's what vectors are. And we'll take a look at how this is going to work, right? Just remember that vectors are always going to have a magnitude and a direction. Well, we got to talk about what's a magnitude. Well, magnitude is the length of the vector. It's the length. So, if we're finding lengths of vectors or lengths of lines, we're probably going to use the distance formula. Or what it was derived from, which is our Pythagorean theorem as well. So we could use one of these two, either a squared plus b squared equals c squared, or we could use our distance formula, right, where we find the distance between the x's, distance between the y's, square those, add them, take the square root. And we're also going to need to find the direction. Okay, and it's the angle that's formed with the positive x-axis. We're going to talk about this in a sec. This is important. Well, first of all, our vectors are written slightly differently. Remember, if I had a line, I would write it with an arrow over top on both sides. If I had a ray, we would just put the arrows on one end. Well, with a vector, it looks kind of like a ray, except we only put the little dash on top to know that it's a vector instead of a ray. And you can see that in the picture right here. Okay, and then the other main point that we just talked about is that the direction is formed off the positive x-axis. So in this example, you can see that this vector AB is at x degrees. It's formed off this positive x-axis with this red arrow. So if I drew another vector in here, let's just say this guy was coming out this way at that distance, I would still use the x-axis to find its direction. So I'd have to start by the x-axis, and if you notice, it goes past 90 degrees. And so some of our degree measures for our directions could be past 90, could be more than 180, could be more than 270. It'll never be more than 360 because that'd be our full circle. And you'll see that in our examples here. So first thing we're going to do with our vectors, we're just going to write them in component form is what we call it. So a vector's initial point, in this case, is at the origin. That's what we call standard position, right? And it's going to move around. To write it in component form, all we got to do is we tell how much the x changed and how much the y has changed. So for example, let's just make this up. Let's just say this guy is at 6'4". So to write it in component form, instead of using parentheses, we used kind of brackets here, like less than and greater than symbols in a way. And I'm still doing my comma, so it's kind of an x and a y, but instead of just writing the x and the y value, we're going to tell how much it changed. Well, where did this start at? It started at 0, 0. So how much did it change in the x direction? Well, it went over 6 units. I can see that right there. So it's 6, and it went up how many units? Well, it was 0 in the y, and it went up 4 units. So in this case, I didn't really have to subtract anything because 6 minus 0 is 6, 4 minus 0 is 4. But the biggest thing is component form, we need to write it with the brackets instead of parentheses, because then I know it has a distance of 6 in the x direction and a distance of 4 in the y direction. Let's try one here. This will make more sense. So write the component form of AB. So once I see component form, I know I'm going to write it with my brackets. Well, here's the trick now. Where does it start at? It's starting right here at -1, -4. And it's going towards B. Okay, so one way to do this, I could count how my x's changed. Well, how far did it go right or left? It went left, what, 1, 2, 3, 4 units. So if it goes left 4, I wouldn't just write 4, I'd write -4. And if I subtracted, I should always subtract from where it ends minus where it began. So for my x direction, I should take -5 minus -1, which in that case is -4. So that works out. And if I did the y's, well, let's subtract first. So where did it end? It ended at B, so -1 minus -4, which is really what? -1 plus 4. So it should be 3, and let's count it off. It went up 1, 2, 3 units, right? So it went left 4, so -4, and it went up 3. Because then I could state its component form as -4, 3. So if I knew that it started at -1, -4, I know to find where it ends. Well, I'd go left 4 and up 3 from that point. It's almost like telling what the slope is in a way. Okay? So just the component form. All right, now let's get a little more challenging. It says find the magnitude. And remember, magnitude, that's just the distance of the vector. And the direction, and remember, direction is always off the positive x-axis. Those are our 2 keys here. Of ST. And it gives me my 2 points. You might have to graph the points. So it starts at S and it's going towards T. It's going towards this way. So first thing, let's find the distance of that. So a couple ways to do it. Right? I could do the distance formula. So to find the distance of ST, it would be the square root of, well, the distance between my x's squared plus the distance between my y's squared. Well, what's the distance between my x's? 1, 2, 3, 4, 5, 6, 7. They're 7 apart. Distance between my y's is what? 1, 2, 3, 4, 5. Between -2 and -7 is 5 units. I could physically subtract the numbers, but I like to just count if I have a graph. It's nice and easy. And well, what do you notice? This really just makes a right triangle right there, doesn't it? So I could just do 7 squared plus 5 squared, and then take the square root, like my a squared plus b squared equals c squared. They do the exact same thing. So ST in this case ends up equaling the square root of 74, and that's round to the nearest tenth with these guys, so about 8.6. There's no units on it, so just 8.6 units or just 8.6. So there would be its magnitude. I got the distance. Well, for the direction, what did we talk about before? It's based off the positive x-axis. So I'm looking at, I know this thing is shifted a little bit, so I'm not looking at this up here. I'm looking just in that direction. So where is that direction of this guy? It's based off its initial point. So really I got to imagine that it's going off this way. I got to base it from right there. Okay? So I'm looking at what this angle measure would be. So it's almost all the way, it's almost a whole circle, isn't it? There's a couple ways I can do this. Okay? A couple ways I can do this. Well, if I take a look, didn't I just make a right triangle when I counted off how far my x's and y's were apart? Right here, I went over like that, and then I went down 5, and I made a right triangle. Well, I know how to find angle measures of right triangles, right? Because I have my SOHCAHTOA. So if I found this angle measure, let's just call that y. I'll just say that's y degrees. If I found that angle measure, I could be able to tell what my big angle is right here. And we'll find out what we do with that. So let's go ahead and find what that angle measure of that triangle is. Well, let's take a look. I know 5 and 7. What are those? 5 is the opposite of angle y, and 7 is the adjacent to angle y. So opposite and adjacent means I'm using tangent. So the tangent of y equals opposite over adjacent. Remember, to find angle measures, we take the inverse tan of that ratio. So the inverse tangent of 5 over 7 gives me 35.5 degrees. That's not my answer. Okay, I need to do something with that. Because my direction is always off the positive x-axis. Well, we just said the positive x-axis, according to my starting point, is right here. So I'm looking at this whole thing right here. Well, I know all the way around, if I went all the way around, it's a circle, right? And circles are 360 degrees. So the first circle is 360. Well, if I subtract what this y degrees is, won't I get what's left of the circle? My direction right there. So if I subtract that 35.5, which was what we had for our triangle, I end up with 324.5 degrees, and that's what this entire degree measure would be. 324.5 degrees. So then I know it's based off that x-axis. If I say it's 324.5 degrees, I know that I'm going almost all the way around in that full circle to find my direction. Okay, I can tell that it's pointed towards the fourth quadrant there. Okay, so that's kind of the toughest part to get used to. We'll do another example here, so hopefully we'll get the hang of that. One other thing is we could just have vectors written without writing their distances and things like that. So a couple terms, equal vectors, that means they got to have the exact same magnitude and the exact same direction. So B and C, for example, if I take a look, B and C, same direction, same magnitude, right? Same distance. B and E would not be, because E is going the opposite direction as B. Okay, so those would not be equal. Parallel vectors, they don't have to be the same direction, but they have to be opposite direction, if anything. So both going up and down, one's going up, one's going down. As long as they're parallel to each other, it works out. I could also say, you know, that B and C or C and E are parallel, things like that. But D and F would not be, because those are going two totally different directions, right? They would end up crossing each other. So those are not parallel. And lastly, opposite vectors, they got to go the exact opposite direction and have the same magnitude. So one example would be B and E. They're going the exact opposite direction and they have the exact same distance or magnitude. And we're going to do something with these guys. Okay, we can either add or subtract vectors. So I got two vectors here, vector M and vector N. Okay, if I want to add them, it's kind of nice and easy. So I'm just going to bring M down here. I have to keep its same direction and its same magnitude, its same distance. And if I'm going to add N to it, all I got to do is put it right at the end of where M was. And then I just connect where I started initially to where now I'm ending. And that would be my new vector. Let's just say, we'll just call it vector P. How about? So there we go. That would be vector P. If I added M plus N, that's what we would get. Okay, let's move these back. So to add them, you just start the one right at the other end. If I subtracted them, kind of the same thinking. Let's just take a look. So I start with M, but now I'm going to subtract N. Okay, so instead of just putting it like that and adding it on, think about this. It's almost like our subtraction rule. I could add the opposite. So let's just make N the opposite. So let's just flip it in the opposite direction. I got to keep the same distance. So I'm pretty close there. So I put it right at the end, but it's in the opposite direction when I subtract it. And now I just connect. I started right here. Now I'm ending right here. Boom. Let's just say that equals P again. So that'd be vector P. Subtracted. So it's just kind of like adding the opposite. So I just change the direction, but keep the same magnitude. And it should be about almost half the distance that other one. Okay. Very good. Lastly, it could be in a story problem. It says, suppose a person is canoeing due east across a river at 4 miles per hour. Oh, that's one other thing we forgot to talk about. Going way back, the magnitude, that length of the vector, that's the speed. The length is the speed. Sorry, I forgot to cover that. So every time we find the magnitude, that's the speed of our vector. So in this example right here, the speed of our vector was 8.6. Obviously, there's no real life situation, so I wouldn't even test that to speed. But in this case, distance and speed are the same thing. So suppose a person is canoeing due east across the river at 4 miles per hour. If the river is flowing south at 3 miles per hour, what are the resultant direction and speed of the canoe? So here you go. You're starting right here. So here's your canoe. Boom. Here's your canoe's vector at 4 miles per hour. Okay? And then you got this river that's flowing south at 3 miles per hour. So this river is flowing south, boom, at 3 miles per hour. Well, what's the resultant direction and speed of the canoe? So that river should affect our canoe, and it's going to push it this way. Should make a nice right triangle for us. Should have a little right triangle. Okay, so I should be able to find my new speed of my triangle. Because, well, I have a right triangle, so I can just use the Pythagorean theorem. And if I notice, this is actually a Pythagorean triple. So I could take 3 squared plus 4 squared and equal c squared to find what that is. But it's a Pythagorean triple, so I should know that it is 5. So the resultant speed of this canoe is what? 5 miles per hour. Okay, so I know it's going 5. Well, direction. Remember, direction is always based off the x-axis, the positive x-axis. So let's kind of draw it in. Here's my starting point. There's the positive x-axis. So I'm looking for which direction? Boom, started off there, that direction. Okay, so it's kind of like that last example. I could find this angle measure, right, and subtract it from 360. Another thing I could do is I could find another triangle. I basically could draw a triangle right here and find this angle measure and add it to 270, because 270 would be 3/4 around the circle. But that just seems like more work to me. So why would I do that? I don't want to do that. It seems like more thinking. Okay, so let's go back. So I need that angle. Well, I got a triangle here, so if I can find this one, I can subtract it from 360, because that's all the way around the circle. So I'm just going to call this x degrees again. Well, I can use any of my information, 3, 4, or 5. I'm just going to use the 3 and the 4. I'm going to use the opposite and the adjacent from that angle measure. So I know I'm using the tangent of x equals opposite over adjacent. So I'm going to take the inverse tan of that ratio, which gives me x. And that's going to equal 36.9 degrees. So there's 2 ways I can answer this. I can subtract it from 360 like I talked about, because remember 360 would be all the way around, right? And I can take 360 minus that 36.9, and I would get my direction, which in this case is 323.1 degrees. That's one way to do it. If I'm using like physical directions like east and south, there's another way I can do this, and we've looked at this before. If you notice, we began by going east, and then we started going south of that. So I could just use that direction that I found. I could say 36.9 degrees and say south of east, because I began moving south of east at that direction, at that degree. So either one of these 2 answers is correct. Right? If I put the 323.1, I do not need any label with it. If I just use that angle measure, I got to describe that it was going south of east. Okay, hope I didn't confuse you too much. I know vectors are brand new to us, so you might have to go look at these examples a couple times or ask me some questions tomorrow.